My name is Tim Murray, and I work on the Android performance team. And we're going to talk today about improving your application's performance on Android. Now, one of the big things that the Android performance team has done in the past year was to optimize the performance of the Google Pixel. We looked at everything on the Pixel, from application code all the way down to the kernel, everything in between. We tweaked things, we experimented with things, we replaced other components entirely. What did we try to do here? What did we do to, what was our focus for performance? Number one, we wanted to hit 60 frames per second all the time. This means that you have to render a frame in 16.7 milliseconds all the time. If you run at 60 frames per second, your app looks fluid. Your app looks smooth and responsive. If you don't run at 60 frames per second, people notice. The phone doesn't feel fast. The phone feels like it's struggling. So that kind of consistency is paramount. You really want to hit 60 frames per second all the time. The second thing we focused on was to make applications start quickly. A user will switch between applications a lot in the course of normal usage. If I'm in Gmail and I click a link that opens in Chrome, I want that to go quickly. If I click a link in Chrome that takes me to Twitter, I want that to go quickly too. Anytime that I'm sitting there waiting for the system to switch applications feels like dead time. It's time when I remember that I'm using a computer as opposed to just interacting with the stuff I want to get done. So reducing the amount of time you spend switching apps makes the system feel effortless. It's really important. That's it. That's what we focused on system-wide for Pixel. We just wanted to hit those two things consistently. If you do these two things, when your device is switching between applications very quickly and running at 60 frames per second, it'll feel fast. But more importantly, if your device runs at 60 frames per second and switches between apps quickly consistently, it does it all the time, the device stops feeling like anything. It stops feeling like a device. Instead, it feels like you're interacting directly with the application. And that's magical for a user. That's really important. But there's a problem with this scenario. We run apps, and apps can be slow. And of course, on the system side of things, we're constantly trying to make it easier to write fast applications and make it harder to write slow applications. But fundamentally, as an application developer, there's always going to be something you can do to make the system not run at 60 frames per second or make your app start up really slowly. The issue is that from the point of view of the user, they don't care that it's one app that happens to run slowly. One app that doesn't run at 60 FIPS or doesn't start up quickly ruins that whole magical feeling of the device. And it reminds them that they're not interacting with an app, they're touching their phone, and then they want to throw their phone against the wall. So today we're going to talk about two tools that we used during Pixel really extensively to analyze performance and help you as app developers figure out what you can do to improve your application's performance. The first tool we're going to talk about is called GFX Info. So GFX Info is a shell command that you can use on the device via dumpsys. And all it does is it tell you about the rendering time for your application. So here we can see that we rendered 223 frames. We get the average frame time, the 90th, 95th, 99th percentile frame time. And then it gives us some idea of why things were actually slow. We use this a lot internally, and we really just look at average frame time, 90th, 95th, and 99th percentile frame time. And that's it. That's all this tool does. It doesn't tell you why your app ran slow. It doesn't tell you anything that you should do to fix it. So why am I up here talking about it? because you can automate it. If you take one thing away from this talk, if you decide to take a nap for the next half hour, just run GFX info at the very end of whatever automated test you're running. And congratulations, now you have a performance test. Now you have a thing you can run regressions on. You can spot regressions in your application. The first time you have a performance regression in your application that you want to track down, this will save you so much time and effort. It will pay for itself instantly. This is how most of the internal Android jank tests work. This is how we track all jank across the system. It's incredibly useful. Please just do it. You'll save yourself so much time. But OK, that's GFX info. That only tells you where your performance is today. It doesn't tell you why your performance is that way or what you should do about it. For that, we have to turn to a different tool, my favorite tool, really the only tool I ever use, systrace. So a lot of developers have tried systrace, and they've told me they have no idea what's going on when they look at systrace. And that's fair. I can stand up here and tell you that systrace is easy. It's not really easy. Systrace is not a CPU profiler. Systrace is instead a system-wide tracing tool. The first thing that means is systrace doesn't care about your app. It doesn't do anything special to your application. It's not going to go peek at your application's call stacks and say, hey, you spent a really long time in this function. It doesn't do that. It just tells you when your application was running and certain events that occur within your application. It also tells you everything about the rest of the system. It will tell you things about the kernel. It'll tell you things about the graphics pipeline. It'll tell you things about the framework and activity manager and things like that. Really, if there's any information you want about an Android device, we have probably surfaced it via systrace. We use it for everything. Just to reinforce how important systrace is, in the past year, I've looked at somewhere over 2,000 traces. We use systrace a whole lot. Now, systrace is not an Android Studio. If you want to get systrace, there are two ways to get it. First of all, it's in platform tools in the Android SDK. You can get a version of systrace from there. What I like to do, though, is I get systrace from the repository where it's developed. It's part of a project called Catapult, which is on GitHub. Catapult is owned by members of the Google Chrome and Android teams. So upstream Catapult is always improving. There are always new features. I usually get top-of-tree Catapult. Once you get that, you'll have this Python executable that you can run, and you can get a trace. Now, how does systrace actually work? What does it actually tell you? Systrace is 3 components. At the bottom is this thing called ftrace. Ftrace is a Linux kernel feature that allows the kernel and user space to write event information into a central buffer. What this means, basically, is that you can get a journal of any event that happened on the system. So the kernel will tell us things like, hey, this process started running on this CPU, or hey, the clocks changed on this CPU. That's great. It's really low level, but we can use it. The next thing above ftrace is a program called atrace. Atrace is an Android program on the device that is installed automatically in the Android image. It's on every device. All it really does is it configures ftrace. But it also configures user space tracing. So atrace will go and turn on all of these different trace points inside of the Android user space. So here we can get things like, do you want to find out what window manager thought about your application? Atrace will turn that on. Or activity manager, or any other part of the Android framework. All of that is controlled by atrace. The topmost layer is systrace itself. Systrace then lives on your host development machine, and it gets the results from atrace, and it wraps those results in a nice HTML file. You get this giant, potentially tens of megs or even hundreds of megs HTML file that contains a trace. So all you have to do to look at the trace is you open the HTML file. It's pretty convenient, and it actually makes sharing traces incredibly easy. Now, the first thing you should do when you decide to start tracing a device is you should look at the categories available on that device. Systrace events are separated into categories, and those categories will vary from OS version to OS version and potentially device to device. In general, the important stuff will always be there. The core stuff that you want as an app developer, we have tests for that, so they'll be on every device. Now, let's actually run a trace and see what that would look like. So this is the command I used for the trace you'll see for the rest of this, this talk. And the way systrace works is you provide the list of event tags that you want in your trace. And here we have sched, which is the kernel scheduler. We have freq for CPU frequency information. Idle will tell us about when the CPU goes idle. AM and WM tell us about the Android Activity Manager and Window Manager. GFX will tell us everything you ever wanted to know about the Android graphics pipeline. View will tell you about the view hierarchy inside applications, which can be really useful. Dalvik enables the trace point for the ART VM. Input will tell you when you're actually touching the screen, and binder driver will tell you exactly when a process is making an IPC call over binder to another process. The last three arguments are special. -t just says we're going to run the trace for 5 seconds. If you omit the -t, systrace will just prompt you to press enter when you want to stop tracing. -o just controls where you write the file, so we're going to write to io.html instead of trace.html. -b is a little odd. So I mentioned ftrace and the ftrace buffer. The ftrace buffer is a fixed size. By default, it's, I think, 1.4 megabytes. And what happens if you fill this buffer, if you have too many events for the buffer, is you'll get a trace, and then at the end, things will just kind of stop happening. You think you ran the trace for 5 seconds, but maybe you only actually have 3.5 seconds worth of events in there. When I take a trace, I always increase the buffer size. So here, I've increased it to 16 megabytes. And for this kind of trace, we probably don't have to increase the buffer size, but it's always better to increase the buffer size and not have to take a trace a second time than be overly conservative with the buffer size. All right, we run this. We now get a trace. What does the trace actually look like? There is a lot going on in this trace. And if you're in the back, I'm sorry, it's probably really hard to see. The first thing to know about the trace is that it is a timeline view. It moves left to right, and you can scroll it left to right. And time moves from left to right. So the left side here is the beginning of the trace. That's 0 seconds when we kicked off the trace. And 5 seconds is when the trace ends. You can move around the trace. You can pan in time with A and D keys, and you can zoom in and out on whatever section of the trace you're looking at with WS. So it's just WASD, like a first-person shooter. The trace also scrolls up and down. So here you see there are a bunch of rows up here. There's this kernel section and then a calculator section. There are way more rows than fit on the screen because there is one row generally for every thread that is run during the trace. So you may have hundreds or thousands of rows in your trace. The next thing to look at when you start using systrace is there's this palette of tools that I have over here in the upper right-hand corner. You can click on these tools. You can also access them with numbers 1 through 4. Number 1 is the pointer. That's the main tool we use when we use systrace. That lets us click the individual events that we see in the trace and get some information about them. And when you click an event, it will show up in the bottom half of the screen like that. So here we can see calculator was running, We see the process ID, we see the thread ID, the priority. We can see when exactly it started in the trace. We see how long it ran for. We get a bunch of useful statistics. You can also use the pointer to select a lot of different things in the trace, which gives you an aggregate view that looks like that. And so this will basically add up all of the threads. Like if I select a region in the kernel section here, this will add up all of the threads that occurred and tell us how much time did we spend in each thread. Well, what was the average time that each thread ran? Things like that. That's really useful. We'll come back to that later. Number 2 and 3 on the palette are for panning and zooming, so they're equivalent to WASD. You don't need to use them. You can use them if you want. I generally just use WASD. The 4th tool, though, is incredibly useful. It is the highlighter tool. So you could select a region of time in the trace, and that region will have a white background, and everything you haven't selected will then have a gray background. You can use this to keep track of the area you care about as you scroll vertically through a trace. So if you find something in one process and you think, something went wrong here, what else was the system doing? You can scroll up and down the trace and know exactly what part of the trace you should be looking at. I use the highlighter constantly. If you start using systrace, you probably will as well. Now let's scroll down and see what else is in the trace. More stuff. So every row in a trace is either a counter or a thread. And down here at the bottom is a thread. These blocks right here are the core thing that you will look at in systrace. These are events. So every systrace event has a beginning and an end. Systrace events can then be nested. So this is a stack that grows down. You can see that here a choreographer event happened, and a traversal event was contained entirely within that event, and more things happened beneath. This is some stuff that's part of Calculator App Startup. And you will see a lot of these as you look through a trace. Each event, it corresponds to an explicit place in the Android code base that somebody thought, hey, maybe somebody will need to figure out that this is happening sometime. It's good to pay attention to these. Now let's zoom in on the beginning of, or at the end of activity start for Calculator. So in this trace, we launched Calculator and clicked a few buttons. Here we are at the very end of activity start. And I zoomed in really closely, and it's still probably hard to see because systrace has a lot of very small UI elements. But there are these colored bars on top of the UI thread here. These colored bars represent the state of that thread at any point in time. There are 5 different states that a thread can be in. Now, if we click the green bar above the UI thread in the middle, we see that at this point, the thread was running. So at this point, the thread is actually running on a CPU. It's running on CPU 1. And if we were to scroll back up to the kernel section, we would see it's scheduled on CPU 1. This is how you can know that your application is actually running at particular times on the CPU. The next state that we care about is runnable. Runnable means that your thread could start running at some point in time. Nothing is preventing your thread from running. It's just that the kernel has not scheduled it yet. There are any number of reasons why this could happen. Maybe there's more higher priority work. Maybe your thread has just run for a really long time, and the scheduler is trying to be fair and give other threads an opportunity to run. There are lots of reasons for this. But if you're seeing a lot of this in your application, it's probably due to thread priority. The third thing that you can see over on the right-hand side of the trace here is there's a red bar. And the red bar is uninterruptible sleep, which sounds a little scarier than it is. Uninterruptible sleep is your thread is blocked on some lock inside of the kernel. As an application developer, there's generally not too much you can do with this. Sometimes it's hardware related. Sometimes it has to do with memory. Usually, if you see a lot of uninterruptible sleep, it's my fault. It's a system problem, so we're probably aware and trying to fix it. But sometimes you can see it's related to memory. You can get some more information about it. The fourth type of state is a special kind of uninterruptible sleep that, as an application developer, you can actually do something about. The orange state here is your thread is sleeping on block I/O. This means that your thread is reading from disk, and the disk hasn't gotten the results back to your thread, so your thread can't make progress. If you see a lot of this in your trace, you're just reading too much data. Try not to read so much data. The fifth state, the last state, is the state you'll see most often, and it's usually white or gray, depending on the background of the trace. It just means the thread is sleeping. The thread has no work to do, so it is asleep. It's not running. The scheduler isn't trying to run it. Nothing is working on behalf of that thread directly in the kernel or anything like that. If you see this a lot and you think that's weird, it's probably due to some user space lock interaction, because user space locks will show up as sleeping. The last thing you can do with these colored bars that is really great is you can select all of them in a region that you care about to get aggregate information. So here we can see we spent so much time sleeping versus runnable versus running. I do this constantly. This gives me a really coarse idea of what the bottleneck is for a particular piece of code. I can take a trace and see, hey, this thread is running. It's on the CPU. It should be making progress, but it's just taking too long. What's going on? It means that it just has too much CPU work to do. If it's getting CPU time and not running fast enough, all you can really do is reduce the amount of CPU work it has to do. Now, if I take a trace and I see that a thread is always in block I/O, then I know it's reading too much data from disk. So don't read so much data from disk. If you're sleeping where you don't expect, it probably means that your application logic is a little weird somewhere. You probably have some weird priority inversion to something, or lock contention that you didn't expect, something like that. Another useful tool on a trace is, I mentioned the input tag earlier. And up here at the very top, there's this tiny little box for input response. And this shows where I actually touched the screen in the trace. So here, I touched the screen, and I guess my finger was down for 28.8 milliseconds. You can use that in the trace, similar to the highlighter. You can use that to orient yourself in the trace. You know what's going on. If you remember what you were doing while creating the trace, you can figure out where exactly you are logically inside that trace. But what if you need more information than this? What if you have a lot of information about what your app is doing logically that you want to get in a trace? Good news, that's pretty easy. So there is a class, android.os.trace, that has two methods, begin section and end section. If you can put a string in begin section, and that will just show up as an event in the trace. It shows up the same as anything else. The only special thing you need to keep in mind here is you need to call trace.endSection from the same thread every time you have a begin section. If you don't have a one-to-one mapping between begin section and end section, your trace will look weird. You will get very weird rendering in your trace, and it's just because you forgot an end section or you had too many end sections. If we take a trace and we want to see the app events, we have to do a little bit more than we did initially. First, we need to specify this app tag as part of the arguments to the trace. And then we have to pass -a and the package name that you care about. Then you just take a normal trace like that, and you open it up, and you see this trace event, which is just whatever you put in your string. If you have logical groupings of work or a logical task that the user is doing, adding a trace event for that is really useful. When I look at large, complex applications within Google, I find that the applications I can debug easily and understand the performance of easily are the ones that implement their own application trace events. I definitely recommend doing it. It's not that difficult, and it will be worth it as you start looking at systrace. It will make systrace a lot more comprehensible. And for reading a trace, that's about it. There's not really that much going on in a trace. It's just sort of what the system is doing at any point in time, and everything that the system is doing at any point in time ends up looking like this. So now what? I don't think most of you probably feel that comfortable using systrace yet. So why would we want to use systrace? What is systrace going to tell us that makes it so useful? Let's go back to the two goals that we had for Pixel. Number one, 60 frames per second. Number two, it makes apps start quickly. OK, yeah, systrace can tell us some things about this directly. But there's an underlying principle here that we should call out. Don't look slow. That's it. That's really the only performance rule there is. The reason why we use systrace is it can tell us where we look slow. And note that I said, don't look slow. I didn't say, don't be slow. This may sound weird coming from a person who works on performance, but for any moderately complex application, at some point in time, you're going to have to do something that is slow. Maybe you're going to do some giant matrix multiply for some reason. Maybe you're going to read from disk. You have to read a large image. Maybe you have to talk to the network, which could take who knows how long. At that point, you want to understand, why did the system end up looking slow when I was doing this? And then what can I do to work around this? You know you have to do this slow thing. What can you do in your application to identify where exactly that slow point happened and then work around it to make the system still look fast? Because that's all the user care about. They don't care if the system is slow or is fast. They just want the system to feel fast. If you do that, it'll be great. Now let's apply that to the two goals that we had. App startup. The basic thing with systrace and app startup is you can use systrace to figure out exactly where your time is going during app startup. Then you can decide what to do about it. And there's no one-size-fits-all advice here. Really, you have to understand what your particular application is doing, what the needs of your application are, and then you can come up with a solution. The first thing that we use systrace for to analyze app startup is view inflation. Here we have this inflate section in a trace. This is from the very beginning of Calculator, from activity start in Calculator. And we have this really long inflate section. But more importantly, we can see the exact cost of inflating every view for Calculator. This is really useful to help you figure out the cost of a view hierarchy or changing a view hierarchy. You can say, is it actually worth 50 milliseconds to inflate all these views right now? Could I do this later? Could I do something else instead? You have to come up with whatever solution is right for your application. But systrace can help you figure out what is actually happening today in your application. So you can come up with those improvements and those ideas for future changes to your app. Another thing that systrace tells you is you can tell exactly when application startup ended from the user's point of view. There's more than just bind application and activity start in application startup. Here you can actually see the UI thread and render thread of your application, which are the two most important threads in making your application run at 60 frames per second. And we know that once those threads have finished for the first time, here you can see the UI thread running and finishing this choreographer do frame, along with the render thread running at the same time. Once that's done, the app is actually loaded and ready for user input. At that point, from the user's point of view, app startup is done. Another useful thing in systrace is the resource tag, res. So you can look at exactly what resources you're loading in your application at any point in time. Usually, loading resources is not a huge deal. Occasionally, we've seen areas where resource loading can be expensive. It's worth checking in your application. It will tell you, just as the name of an event, exactly what resource you're loading and how long it takes. And again, you can figure out, is it worth loading this resource right now? All right, let's move to jank, because that's the more fun one. Fixing jank with systrace is a two-step process. Number one, you need to figure out where the jank actually happened, because maybe you can spot every time the system doesn't run at 60 frames per second. But I've been doing this full-time for a while now. I can't even do that. So systrace can help make it really obvious where exactly you dropped a frame. The second step that you use systrace for is working your way backwards from the dropped frame to what actually went wrong. And then you can figure out what to do about it. So here we have a UI thread and render thread again in an application. And we're running the thread, or the application normally. It's not a janky frame. It's just normal 60 frame per second rendering. The UI thread is the main application thread. That's what actually gets input events from system server. Render thread actually gets information from the UI thread and sends that to the GPU. This means that in order to display a frame on time, the UI thread and the render thread have to complete within 16.7 milliseconds every time. This gives systraces a nice kind of rhythm. You can get used to this rhythm when you open a systrace and say, oh yeah, dropped a frame there. Because you can tell it didn't quite line up. It makes it easy to spot where the UI pipeline didn't run at a full 60 frames per second once you get used to this. Now, if that's not enough, you can look at Surface Flinger. So we don't have time to go through the full Android UI pipeline, but the high-level overview is your app will render a frame, and it will send that frame over to Surface Flinger. Surface Flinger is a system service that will take whatever app is rendering on the screen, and it will combine that with the navigation bar and the status bar, and actually send the resulting full, completed, composited frame to the display to show up on the screen. What this means is that Surface Flinger is the central source of truth. If Surface Flinger thinks you hit your frame deadline, you're running at 60 frames per second. If Surface Flinger says you didn't deliver a frame, you know you didn't actually hit 60 frames per second. And here, the way we can do that is we have a counter here. There is one counter per application in a trace. This counter here is alternating between 0 and 1 for how many frames does Surface Flinger have from this application that are ready to be displayed. So you know that if the counter goes to 0 for more than 16 milliseconds, you have definitely missed a frame. This is the ultimate way to know whether you had jank in your application or not. This helps us spot where the problem is. It helps us know where you actually dropped the frame. So what do you do when you know where the problem is? You're going to work your way backwards. So we're going to look at Surface Flinger to work our way backwards. We're looking at Surface Flinger just as an example of a relatively simple chain here, because application chains can be more complicated. We don't quite have time. But usually, you want to know why something woke up. So we have a running state in the application, and we want to know what made it runnable, because that will tell us why the thread woke up in the first place. So here, I clicked the running state on top of Surface Flinger, and I can hit the left arrow, and I can see the runnable state. Now I have the runnable state selected, and I want to go ahead and highlight that. You can highlight anything you currently have selected with the M key. Now we have a nice little bar showing what we're looking at in the trace. In this runnable section, we have an additional argument at the bottom here. And it says, wake up from TID 529. This means that the Surface Flinger thread was triggered by thread 529. Now, I don't know what thread 529 is, but I do know that thread 529 must be running at this point, because if thread 529 wasn't running, it couldn't have woken up Surface Flinger. So I can scroll back up to the top of the trace to see what is actually running on the CPU. And I see this thing, event thread. So I'll click event thread. And event thread is part of Surface Flinger. It's another thread inside of the Surface Flinger process. And now I want to know what woke up that event thread, because I'm working my way backwards to figure out why Surface Flinger woke up at all here. So I'll scroll back down and find event thread inside of Surface Flinger. And there's the actual thread state for the event thread. We just have that little colored bar to show that it's running because it doesn't have any events during that time. We can click the runnable section of the event thread and see that it woke up from thread 4568. Now, I cheated. I know what thread 4568 is. It is the display sync thread that is also in Surface Flinger. So let's go to that one and see what woke up the display sync thread. That's right down there. We click it, we see wake up from TID 0. TID 0 is a special thing in a trace. And all it means is that whatever thread you were looking at was woken up by an interrupt of some sort. It was woken up by an interrupt handler. Usually, this means a timer expired. This makes sense for Surface Flinger. Surface Flinger will run every 16 milliseconds. So a timer expired, woke up this display synchronization thread, which in turn woke up the event thread, which then woke up Surface Flinger. If you see this in your trace, it usually means that some timer expired and woke up your thread, and that's why you're running. And that's it. That's the basics of what you need to know to actually get somewhere with systrace. Take some traces of your application and just try to see what's going on. Look at the system, look at how frames are being drawn and sent to the display, and how you're getting touch input from the server. This kind of tracing backwards via the runnable state is most of what we do to understand how the system fits together. And you can use it to improve your applications as well. Now, if you want a lot more advice on what you should do, as opposed to how to understand what's going on today, I recommend you go to there's an additional Android performance talk specifically on the UI pipeline that Chet Haas and Chris Craik are giving. It's at Friday at 1:30 p.m. So definitely go to that. I know they're going to talk a bunch about recycler view and optimizations there, which is always a popular topic. So that's it. Thank you.